Okay, good afternoon. My name is Eric Leupold. I'm an administrative specialist at the Teaching and Learning with Technology Help Desk at Rutgers. And on behalf of Rutgers University Online Learning Conference, I'm delighted to introduce Paul Takastov from the professor at Rutgers Department of Food Science. We're pleased to have him present the virtual remote labs for teaching a lab-based course on food technology today. During the presentation, please use the live Q&A to ask any questions of the presenter. And at the end of each presentation today, there will be a short survey displayed. Any feedback you can provide is greatly appreciated. And Paul, on to you.
Yes. Okay, thank you for the introduction. Good afternoon, everybody. It was a challenging year, and for me, teaching hands-on engineering course, to switch to the fully remote lab, it was very, very difficult. So the course is, we will talk today about what tools are available, the virtual and remote labs. I'm going to describe the proposed framework, and we'll go through one lab case study, how we did it, and see what we got at the end. So the first about the course. This is the core course for the food science. Our students work in the industry for the major companies like Mars, Unilever, Pepsi, and department, it's one of the top in the country. And one of the core competencies for the students, it's the processing, food processing. It's the manufacturing, high volume manufacturing. And this is very challenging course because it requires a lot of quantitative math skills, critical thinking, problem solving, and certain amount of the creativity. Their calculus, physics, and introductory courses are prerequisites for this course. And this course is mandatory, it's full credit course, and the lab is about 30% of the course. It's very lab intensive. And there are certain learning objectives. And actually, we are not educating our students to work on the manufacturing floor, but they have to understand all limitations and all underlying conversions within the food, and to be able to operate an equipment in order to work in the food product development, where most of our graduates are working. So this course usually requires significant amount of hands-on experience. So the trade, and suddenly last year, almost on the fly, we have to switch it to the remote operations. Remote labs in the engineering, and especially in the food engineering, is not new. It's actually ongoing modern technology, which became available with the development of the informational technology and networks. And actually, remote lab is the use of telecommunication to remotely conduct real or virtual experiment at the physical location of the operating technology. So technically, it will reduce the requirements to come into lab. So there are several benefits associated with the remote labs. First of all, even now we have and we have several students who stay in their countries and they cannot come to our campus, to our lab, because of the pandemic restrictions. Therefore, we have to relax geographical constraints and actually allow students who cannot attend lab to get relevant experience. The second issue I'll show later, the processing labs are quite different from other labs. We are working with pilot scale equipment with a capacity from kilograms to 100 kilograms or gallons. So it's pretty large equipment. Therefore, we cannot organize small stations for individual learning of the students. Usually students working in the group with one set of the equipment with one unit operation at the time. And therefore, the design of the remote lab would provide so-called scalability opportunity. So several students will have more access to the equipment, contrary to the actual hands-on labs. Secondly, it potentially can improve quality of the experiments, because if we introduce elements of the modeling or computer-based analysis of the data, students can repeat data analysis with different variables and actually exercise more. It's possible to improve effectiveness because they can be more flexible and they can repeat several times the exercise, and I'll tell about this a little bit later. And honestly, it improves safety because this is high power equipment we use, and with the high voltage, with the motors of the range of kilowatts, with a lot of moving parts, with hot surfaces. So the safety is the real concern. But there are significant disadvantages which technically diminish all benefits of the remote labs. Of course, the disadvantages highly depend on the type of the lab and topic area, but the general, if we compare to the proximal in-person labs, is the lack of hands-on experience, is the lack of troubleshooting experience, which is actually the main learning exercise, and lack of the equipment setup experience, especially for the students where this is maybe the first time in their life when they have to mechanically assemble relatively large scale equipment and practice and check how it's assembled, how it works, how it operates, the vibrating, noisy, high temperature environment. For some of them, it's quite shocking experience, but this is a very, very learning experience. So first of all, let's go, what do we have now? We have virtual and remote labs. So there are a lot of possibilities to create good learning environment and provide remote practices. More time, and actually if we can design something asynchronous, no schedule, which is quite beneficial. So there are two types of the labs that are available on the market and that you can find in the literature. The first is the virtual lab, which is based on augmented reality. It's beautifully designed, provide real-time feedback control. So technically students have extended their hands with the computer and they can perform experiments. And beautiful graphic, which will provide true immersion into the lab environment. And beauty of this approach that technically almost endless number of users and no limitation for the geography. of such approach. First of all, it's very low availability for the specialized lab. If you check the market, most of the designs are available for the basic chemistry course or for basic physics course. That's it. So for high level, 400 level courses, for specialized engineering technology based courses, no such labs available. The second, despite the graphic, the actual feeling of the equipment, the feeling of the lab environment, the pilot processing plant environment with the light, noise, surrounded by the machines, it's completely different feeling. The second type of the labs is the virtual labs, based on the computer simulations. Some labs actually would allow full simulations of the processing robotics, or which is famous set of the food engineering labs developed by the Paul Singh from the UC Davis, based on the computer simulation, the numerical simulation of the processes. On the right side, you can see the heating of the food container for the pasteurization and retorting operations. They're beautifully designed. They provide relevant set of variables, so students can check the process variables, they can change it and see the outcomes. They can perform some mathematical analysis of the data, and actually will pretty strong understanding of the processes and what's going on with the food materials within the processing equipment. However, there is no actual running experiments. There is no actual exercise. So what about our labs? It's a lab-intensive course, usually require 3-4 hours lab time per week. Besides the hands-on experience working in the pilot plant, it requires quite a bit of quantitative skills for the data analysis. And even for normal workflow, we have some difficulties due to limited number of resources, because we cannot run experiments many times due to capacity of the equipment. It's cost prohibitive. We have limited time for the lab exercise because of the length of the experiment processing. For example, retorting would require 3-4 hours for the canned food, and many other experiments would require hours of time, and the limited number of stations due to size of the equipment. So what we can do with this? So we have the whole spectrum of the possibilities. On the one hand, on the right, we have traditional in-person lab, when instructor with the teacher assistant will help with the setup and guide the students, and students perform the work. So this is traditional lab with very close interaction. On another hand, on the other side of the spectrum, we have computer-based virtual lab. Students are sitting in comfortable environment and just perform the simulation. So what else? We do have remote lab, which require very expensive specialized equipment to perform loading, uploading operations, set up experiments, so robotics. And it's very difficult and very expensive to introduce industrial grade robotics and attach it to the industrial type equipment. So this option simply is not available. Is this option used widely in the computer science, in electrical engineering, maybe for some chemistry experiments, but not in the processing labs? What about another option? Can instructor run the lab and show? Yes, it's possible, but this is the demo type lab. So students are passive learners. They observe, they can work on data, but there is no experience. Can we find something in between which would combine benefits of the virtual remote labs with the interactive learning which happens in the traditional in-person labs? So we decided to work on this issue based on to introduce active learning approach. So when students actively engage in the class activities to promote analysis, synthesis, and evaluation of the content. And our major efforts done on the focus on the problem-based learning and cooperative learning. So we utilize the following principles of the active learning as the foundation for lab design. First of all, to set up labs that will be challenging for the students, but will be completely correspond with their background. The second, the lab exercises should be based on the fundamental class materials and would require prior knowledge from prerequisite courses. Promoting practice focused on learning from errors, and I'll show how I'll do it. And connecting new information and actually work based on the engineering principles. No qualitative analysis. Everything must be quantitative. And actually, this is not one-time effort. This is the continuous exercise which strengthens students' skills during the entire semester through several lab exercises. So our approach is to improve the lab efficacy by the design of the new set of education material, redesign the lab so it will be inquiry-based, design lab in the way that it will be interactive based on the hybrid remote procedure, intensive design of the online and desktop-based software for data analysis, real-time data, and real-life lab exercises. So our framework is based on the focus of active learning, which means active participation. We move from the instructor's demo to the student-guided lab exercises, guided group data analysis, continuous interactive test of the student's knowledge through the mini quizzes, inquiry-based questions, and continuous interaction with the student during lab exercise. And this is we consider as iterative learning. If group or students submit report that would not satisfy the requirement, the lab report will be returned to the students and they should work on the errors, on the analysis, and work on their more comprehensive description and interpretation of the data and the experiments. So what is the workflow that we proposed and implemented? The distribution of the lab materials, it should be done at least in a week before the lab. Before joining the lab, there will be online quiz which done through the Canvas. After that, live discussion about the safety. Even the students cannot really be in the pilot plant environment. They have to learn about the safety and actually learning about the possible danger and the precautions before doing experiment will help them to understand the environment. After that, questions about the lab protocol, the detailed questions, what you will do in the lab, what will be your next step, how you will assemble the equipment. And after that, the camera placed in front of the equipment, which is disassembled at the beginning of the lab. After that, professor and teacher assistant, they are not actively interacting with the students.
Excuse me,
Students
Paul.
direct.
I just want to
Yes.
let you know there's 2 minutes left in this portion of the session.
Yeah, students direct what to do, and based on their directions, we are performing the lab exercise. After that, data collected and the experiments performed. So as example, the food processing lab size reduction. The students introduced to the equipment, and after that, in front of them, teacher assistant, based on the student's request, assemble the equipment, exactly parts what they say, the process, the material, exactly as students say, and share the data in real time. After that, students in group, under the guidance, they perform data analysis using different tools and software, check the theory and experiment, and submitting their report. Reports were analyzed and assessed based on the rubrics, and if reports were substandard or unacceptable, they will be returned to the students. In that case, we achieve pretty high output and very good, actually surprisingly, much better students' review and students' satisfaction with the course, and much better evaluation of their quantitative skills and knowledge. So we're thinking to continue such procedure even when students will be allowed to join the labs in person.